Today we're gonna fix the behavior of our camera once and for all. We're gonna make it smoothly follow the player and turn with him just like in the real game. So let's do that. Go to the scripts folder and create a new C# script and let's call it CamLogic and attach it to the main camera game object. Open up the script in Visual Studio. And before we write any code, we need to think about the logic that's going to drive the behavior of our camera in a simplified 2D diagram, just like we did with the player's logic. So, I've created this diagram that's going to step through how the camera should behave in the game with respect to the player. The first thing we want is for our camera to be constantly behind the player as shown in the diagram with some fixed distance, say 5 units. This means that the position of the camera at any given time has to be the position of the player minus that fixed distance. So as the player's position changes, so does the camera's, and the camera's orientation or rotation is simply the rotation of the player. If the player is facing north, then so is the camera. If he turns west, then so does the camera, and so on. Now let's program this bit and give it a try. The first thing we need to do is grab a reference to our player's transform component here in our script so that we could access his position in the scene. So type public transform T player transform. This public keyword means that this transform variable can be accessed from outside the script. Public and private variables are a key concept in object-oriented programming, and they are used for data hiding and protection. By default, all declared variables in C# are private unless otherwise stated. Now let's go back to the editor and click on the main camera game object. You can immediately see that there is a player transform empty field in the inspector window. Drag the player's game object onto it, like so. Now the player's transform component is stored in this player transform variable. Let's go back to our CamLogic script in Visual Studio. Let's delete the start function. We don't actually need it in the script. And also create a public float, which we will call fixed distance. And we made it public so that we could initialize it from the inspector window. Now let's go back to the update function and code our camera behavior. And you don't actually need to copy the following piece of code. It's gonna actually get deleted because it's gonna run into some problems, as you'll see. But I'm gonna do it because you'll learn some things along the way. First, let's set the rotation of this camera game object equal to the player's rotation. Type this.transform.rotation equals player transform.rotation. So set the rotation of this game object equal to the rotation of the players, which is stored in the player transform variable. And based on that rotation, we're going to position the camera in the scene to be behind the player, just like we said we would do in the diagram. So let's check the rotation of the camera, which again is equal to the player's rotation. If this.transform.AllAngles double equal sign, this expression here just accesses the angle around the y-axis. So if this angle is equal to 90 degrees, then the position of this camera is equal to the player's position minus the fixed distance we've specified. And we're putting it in a vector 3 form because the position of the player is stored in a vector 3, and we can always subtract like quantities in C#. Also, we're operating on the x component of our camera position because the player and by extension the camera are in the east direction when this angle is at 90 degrees. Now let's repeat the same process for the west direction in an else if line, only this time we'll add the fixed distance because the west direction has negative values. Finally, else the camera must be north, in which case just subtract the fixed distance from the player's position in the z direction to get the proper camera position, which is to be constantly behind the player. Let's save our script and give it a go in the editor. First, let's reset the transform of the main camera. And let's scale up the plane by 5 units in the z direction and 5 units in the x direction. Let's bring the other side of the plane under the player's feet by offsetting its Z position by 25 units. Also, let's quickly apply some texture to the plane from our hand-painted textures folder so that we could see the textures changing as the camera follows the player. Let's not forget to initialize our fixed distance variable from our inspector window of the main camera game object. I want to make the camera to always be 5 units behind the player. You could choose a different value that suits you if you wish. Save and hit play. Okay, the camera seems to be following the player, and perhaps the height needs some adjustments. Our camera seems to be doing what it was told to do. However, we can clearly tell that the movement of the camera in the scene is a little bit jittery. And also, when the camera changes its rotation, say from 0 to plus 90 degrees, it's abrupt and instantaneous. We want it to instead be smooth and gradual. To achieve such a result, we're going to use a mathematical concept in Unity called linear interpolation. Don't let the name scare you. Its implementation in Unity is just a single line and no more. So let's go back to our CamLogic script and delete the bit of code that we've just written in the update function. I've written it so that you appreciate the importance of linear interpolation, as we will see in a moment. First, let's go up here and declare ourselves 3 floats. Start rotation angle, which is gonna start the camera's rotation around the y-axis. End rotation angle, which is gonna keep track of the player's rotation around the y-axis. Finally, final rotation angle, which is gonna output the smoothed out or interpolated angle of the camera. Now let's go to the update function and set the start rotation angle to the value of the camera's current y angle. And let's get the player's current y rotation angle and store it in the end rotation angle variable. Now let's perform a linear interpolation between these two angles and output the result to the final rotation angle variable. So type final rotation angle equals, and we'll use the lerp angle method from the mathf class or structure. Lerp angle is just short for linear interpolation for angles. Then open a pair of parentheses. And this lerp angle method takes in 3 arguments or inputs. The first is the start value, which is just going to be the current rotation of the camera around the y-axis. The second argument, separated by a comma, is the final value that we want this first value to transition to, which is just the player rotation angle around the y-axis. The final argument of this method is the step size of the gradual transition between the first and final values, i.e. how quickly or how slowly this first value should transition into the second value. And there could only be one logical choice for this transition value, which is time.delta time, because it's the timestamp between each frame. And we'll also multiply it by a float that we haven't yet created called rotation factor, because time.delta time is too slow. Now this is just the value for the y angle. We need to turn it into an actual rotation in the scene by converting it into a quaternion, because as we've said before, Unity implements 3D rotation of game objects using quaternions. Now let's start a new line and create a quaternion variable called final rotation and set it equal to quaternion.ola, open a pair of parentheses, 0, final rotation, 0, and put a semicolon. Now this angle value has been converted to an actual rotation in Unity. Let's declare the rotation factor float up here and make it public as well so that we could easily adjust it from the inspector window. Now let's go back to the update function and position the camera behind the player in the scene. First, we need to set the position of the camera equal to the position of the player. Once we have this new position of the camera, we need to subtract the fixed distance we have specified above. So type this dot transform dot position minus equal, and you know what this sign means. It just means subtract from itself. Final rotation times vector 3 dot forward times fixed distance. Terminate with a semicolon. This expression here is just some clever quaternion math that basically fixes the camera behind the player with this fixed distance. It's basically the same as, let's put a comment. And if you remember at the beginning of the tutorial, we had to use an if statement that checks for 3 conditions so that it can position the camera properly in the scene. We've shortened it to a single line. Math and quaternions are really powerful if you know how to use them. Okay, let's write one final line that's gonna make the camera transform stare at the player's transform in the scene. Type this dot transform dot look at, open a pair of parentheses, player transform. We want the transform of this game object to always look at the player's transform. I've included a video made by Unity that goes over how this look at method works, so be sure to check the included articles of this tutorial. Let's also change the update function to late update. This late update function is a predefined function in Unity, and it's almost identical to the regular update function, except that it gets called after the regular update function. And we want that, right? Because when we access the player's position here, the player controller script could still be working on executing the player's movement code, so we might need to wait a little before accessing his position in this script. Now save the changes and let's go to the editor and give our game a run. Click on the main camera game object, set the rotation factor to 10. Let's set the camera 5 units behind the player to get it ready, and elevate it by 3 units. Save and hit play. Okay, the camera is following the player. Let's turn left, and you can see that the camera is turning smoothly to the left. Oops, our player fell down. Let's try that again. North, west, north again, and then east. I like this. It's working perfectly. There is one final thing that we need to add to our camera behavior, and it's its height behavior. We want our camera to jump with the player, so that when we later program the player jump, our camera is ready to go. So let's go back to the ComLogic script and code this behavior. And it's very similar to the angle calculation. First, let's create 2 public floats, which we will name height and height factor. Next, let's declare 2 private floats and call them current height and wanted height. I think you can see where this is going. In the late update function, let's assign the vertical position of the camera to the current height variable. And then let's assign the height of the player to the wanted height variable, plus some fixed distance provided by the height variable. This way our camera is towering over the player, just like in the real game. Now let's perform a linear interpolation between the current height and the wanted height. Type current height equals mathf.lerp, open a pair of parentheses. This time it's just lerp as opposed to lerp angle because we're interpolating regular floats, not angles. Let's put the current height for the first argument and the wanted height for the second argument. And we want to transition from the current height to the wanted height in a time.delta time steps multiplied by the height factor. Now let's update the position of the camera with the new interpolated height value. Go to this line and type this.transform.position equals new vector 3 this.transform.position.x, comma, current height, comma, this.transform.position.z. Save the script and go back to the editor. Now let's initialize the height and the height factor variables from the inspector window of the main camera game object. We want our camera to be 3 units higher than the player, so put a 3 in the height variable field. You could choose a different height if you like. And for the height factor, I'm also gonna put a 3. Make sure that you save the changes in the editor. Let's hit play. Okay, on the whole this seems very similar to the real game. The player is turning smoothly and the camera is fixed behind him in every direction. And you can see that the camera is staring down at the player. Similarly, if the player were jumping up, then the camera would be staring up at him. And that does it for the camera script. It's 100% complete. We'll never deal with it again in this course. So our tempo run game is really coming together. And in the next tutorial, we're gonna make our player run on infinite forward segments. Thank you.